Hello everybody, this is lecture 4. Today I will speak about the BN junction in a different device. I am Amr Abdul Bari with Nearest University Electrical and Electronic Department. So in chapter 4 of electronic devices by Floyd, he introduced here the other type of BN junction device, which is a very important device, BJT device, bipolar junction transistor. So previously we speak about the diode. Now we will speak about the transistor and how it is work, and after that in later chapters the circuits that use transistor. Okay, so a transistor, there is many different type of transistors, but one of the basic one, the basic transistor is BJT, bipolar junction. Bipolar junction is this one that may be connected of NBN junction or BNB. So it has 3 region instead of 2 region in the diode. 3 region, we connect each one of them, remember that, and we call it the emitter, this one, we call it the base, this one, we call it the collector, this one, and we maybe name it with the letters. Okay, so in the bipolar junction, this is, we call it NBN transistor, and this is, we call it BMP. But you remember that this is the emitter, this is the base, and this is the collector, EBC. And between each one of them there is a BN junction. Okay, so base collector junction and base emitter junction. Okay, so the base is very thin and compared to the other two, and lightly doped region. Doped meaning here that we insert the other type material that making intrinsic material, that making this material B or N material. Okay, so we doped very lightly compared to the other regions. Okay, the emitter is heavily doped, but very not very large. The largest area is the collector, and it is moderated doped. Okay, so this is the collector, which is the largest area, and the thin area is the base, and the moderate area or the in between medium, this is the emitter. Now let's see in the normal operation. I want to make a normal operation for the transistor to work. In the normal operation, I should keep this junction between the base and the emitter in forward biased, and the other junction in reverse biased. Okay, so in forward biased meaning that it should cross the 0.7 volt. Okay, so in NB junction, NBN bipolar junction transistor, this is N, this is P, this is N, so it is should be like this. I connect two external DC power here and here, these two, so it should be connected in this area, this way, so we save, or we have the base emitter forward biased and the base collector reverse biased. For the other type, for the BNB junction, it is different. So you see here we make reverse the voltage, so maintain again here a forward bias and here a reverse bias. Okay, now let's see the termination or the notations here, the symbol here for NPN. We make the arrow to the out for NPN junction, because this is point to where the emitter current go. So here in this NPN junction, the current come from the collector and from the base, and we have IE equal to IC plus IP. IP normally is very small current, but this is a normal equation. For the BMP junction, it is reversed, so the emitter come from here and it is cut it to two small, very small base current, and the rest of the current go to the collector. Okay, so it is the same hole. Okay, so here you see that this is the direction of the emitter current. So you mean that if I draw this symbol, I hint or I mean that I use BMP. For out it is MPN. Okay, for BJT junction or BJT transistor, there is a curve like for diode. The curve here, it is this curve. You should remember this curve because we always work with the curve. We call it characteristic curve. It shows the relationship of the three transistor current: the emitter, the base, and the collector. Now, as you see here, the curve have the first area from A to B. This is, we call it the saturation area. Saturation area where you start with the IC with 0 until you reach some point, okay, which is like acting like a resistance. It is linear. Okay, then we have the active region. As you increase the current, it is dependent from the voltage, the VCE, collector emitter voltage. So it is increased, and almost the IC is the same. Okay, between the point P and point C. Okay, it's almost flat. Okay, then we have the breakdown region. After C, this is the breakdown region. Okay, which we don't normally work in this area. Now, where is the IB? Where is the P current? Okay, so here, as you see, the curve, it is working with the collector and the emitter. But when you set up different values for the base current, you see a different family of the collector curve or the characteristic curve. As you increase the IP value, you see that this curve go up, and there is a difference here. At 0, if the IP is 0, there is a cutoff region, so there is nothing work. The transistor doesn't allow any IC current to come across. So this is, we call it a cutoff region. There is a ratio that we use normally. We call it the ratio of the collector to the base current. So IC over IP, we have beta DC. This is a very important ratio that we use in the characteristic of the BJT transistor. Okay, so it is, if you read here where is the beta DC, it is almost identical or almost the same everywhere here. If you divide the IC over the IP, as you increase the IP, the IC increase, so this is keep the same value. everywhere. Okay, so let's say an example. I want to know what is the beta DC for the transistor shown here. So you take any value for the IP and you see the corresponding IC, and then you calculate the beta. Then in the middle here, he take in the middle here IP. It is 30 microampere, and the corresponding one, it is 5 millimeter. Then 5 over 30 micro, that is a 167, which is doesn't have any unit because it's a ratio between two currents. Okay, now the cutoff region or the cutoff condition, where there is no base current and extremely in practical there is no current here, but there is a very leak current in the collector, very small, extremely small leak current that come from the collector to the emitter. Okay, so neither both of them neither forward nor bias. Both of the base emitter or base collector in forward or in forward bias. So both of them are off in the current in the cutoff region. In the saturation condition, there is the maximum collector current that we can reach corresponding to the IP. There is no other after that. So determined by the external circuit. This is the circuit that determine the value of IP according to the VCC and the IC here. Okay, so in saturation, an increase of the base current has no effect in the collector circuit, this circuit. So the relation IC equal beta DC IP is no longer valid. Okay, so to calculate the voltage here, we see that VCC, this one, minus the current IC multiplied by the RC, this resistor, you get what is left for this place. Okay, now let's see what is a DC load line. The DC load line is the line that's connecting the saturation point by the cutoff point, this line. Okay, so the transistor characteristic curve are shown here and superimposed on the load line. This region, the saturation, between the saturation region and the cutoff point, we call it the active region. This is place, this region where it is, we call it active region, as we see before. Now let's see an example. What is the saturation current and the cutoff current voltage for this circuit? So assume that VCE is 0.2 in the saturation, VCE current voltage. Now let's see for first the I saturation, the current IC at I saturation. You remember that you will take the VCC minus the 0.2 that we have for saturation here, and you divide it by the RC to get the I saturation. Okay, and you get this value. Then we here have if this transistor is saturated or not. To know if it is saturated or not, we should calculate the IP. Where is the IP? So we should see here the IP, it is working or not. So maybe it is in it's not working, all the transistor. So VBB, this one, minus 0.7 over the this resistor, we have the IP. Then we get the IC according to the value beta IP. So IC equal beta here he give it you 200 multiplied by the IP, by the voltage in the current in the base, then you get the IC for this the IC now for this transistor, which is 2.09. so the IC here, it is less than the saturated value, so it is not in the active, not saturated yet, not this transistor didn't reach the saturation point. This the current where it reached the saturation point. If you see here, this is the saturation point, so the IC is still here in this point. Okay, it doesn't go up after the saturation point to reach this this region. Okay, now let's see something else. The data sheet. Yes, data sheet is very important because it's given by the manufacturer of the IC of the transistor that you have, the BJT transistor, and giving you all the information that you need to work in the normal condition, or the condition that your transistor can work on it. Okay, so it giving you the beta, which is given as HFE. Here, this is a name of a transistor, a commercial one, and giving you a beta according to the IC from 100 to 300. So it is very important to understand and read the data sheet. There is another quantities that you should understand and know. We use VCE capital here, capital letter in the subscript, to understand that this is DC quantity. Okay, and uppercase here. So we use it as a lowercase and italic to understand that this is AC quantity. Okay, because maybe our time varying signal, so not DC quantity. Now we have some internal resistor in the transistor. We name it as a small, lowercase, and with a prime here, RE prime. So this is internal transistor resistance, and the external resistance we name it as RC, R capital resistance, and with capital or small lower case according to AC or DC. So remember these notations, because we didn't we use notation normally to understand some or to use it in the mathematical calculation, the calculation of the voltage and current and resistance in the circuit. Okay, now the one of the most important application for the transistor, BJT transistor, is the amplifier. We use it as an amplifier to amplify the AC voltage. Okay, so it converts some of the DC voltage here to increase the AC that is applied to the emitter, to the base. Okay, so the signal that we see here in the VC, it is more amplified. So this is the input and this is the output. As you see here, it is higher voltage, it's amplified than this one. Okay, and inverted. Now it is inverted but is amplified. So another important application of the BJT is using it in switches. So where there is a cutoff, when it is in cutoff, there is no current at the IP, at the base, there is no current, then we use it as off or open circuit, is open switch. Where there is a voltage here, current here, and of course a voltage, so there is there is a bias here, forward bias, and my transistor connect, and there is an IC that come across the transistor, then we use it as a closed switch. Another one, or another type, important type of the transistor, is the photo transistors. Photo transistor is working differently. It is not only in the normal transistor, it is working according to a current or a voltage applied to the base. Now here we apply a light. So when there is a light in the base, then there is a current, and then the switch on, or the transistor, there is a forward bias, and the transistor work. Okay, and if you remember photodiodes, it is the same idea. It is receiving some lights from outside, and then it is working. There is a current inside the diode. The photo transistor have a more important, that have a more gain, and it is more sensitive to light than the photodiodes. Okay, in typical circuit, the base is left open, so until there is a light. However, in this circuit here, it is closed and the voltage is maximum, and when there is a light, the voltage is dropped, and as light increased, and until it is not connecting anything. So it is according to the circuit that you use. It have the same or have similar characteristic curve, but instead of using an IB, there is a light, light flux to the base here. Okay, and we measure it in milliwatt per centimeter square. Okay, and when there is no light, there is dark current or cutoff region. Okay, so this is one of the circuits, and it is controlling or switching circuit, controlling a relay here. Now if there is a light here, the question is either transistor on for the circuit when there is no incident light. So when there is no incident light here, then this is off, and the normal Q2 is working because it is in forward bias. There is here in the base, and there is a current on the relay. Okay, so the collector current in Q2 causes the relay to be energized, because there is energizing here in this relay coil. Okay, when there is a light, then this is connecting to the ground zero, then there is a bias here, it can't saturate it, or it can't be sufficient for a forward bias, and there is no IC current, then this coil is not energized. Okay, there is another application for photo transistor, the autocouplers. This is another. We put here a LED that emits some light, and in the other side we have a photo transistor that receives this light. There is the current transfer ratio, or CTR, which is measuring the efficiency, measuring how much the output here to compare to the input, which is typically from 50 to 110% for standard autocouplers. Autocouplers have applications in the traffic controller, where we want to we don't want to have the switching circuit to be connecting directly to the circuit of the lights here. Okay, so we want some isolation. It is similar to the relay, okay, in the concept. So there is no connection between the primary and secondary circuits, or the controlling or switching circuit, and the power circuit, or the application, or the light in this case. Okay, this is another application, of course. Now this is a sample of the common transistor package that you can see it in the commercial, in the electronic device. And you see here different shapes, and of course it have 3 terminals: base, emitter, and collector. Of course they have different characteristics and different data sheets. So you take the name and search for the data sheet, and you understand more about the transistor that you have in your hand. One of the most and basic tests for the BJT is to test the voltage in the BN or BNB junction between the emitter and base, and between the base and collector. It should be close to 0.7, and if you repeat it, you should see a value that is very close to BN junction working voltage. Okay, and in the reverse you should see the reverse biased. Okay, so what I am speaking about today, that we have something called bipolar junction transistor, which is connected by a 2PN junction, maybe in BNP or NPN. It is consists of emitter, that is the most heavily doped of the 3 regions, and a base, which is the thin and lightly doped compared to the other regions, and the largest region of all of them, but moderated doped, of the PN junction, or the semiconductor regions. This is, we call it collector. We have something that we measure, or a ratio between the DC collector and the base current, from which is a ratio. So we have an area or a state of the BJT, we call it saturation, where have the current or the collector current reach the maximum value and is independent of the base current. A cutoff region, which is non-conducting state or off state for the transistor. And last thing is a different type of the transistor, photo transistor, which is, instead of using the base current, using by a voltage, external voltage provider, we use a light that is striking on the which is using semiconductor that is more sensitive for light. Okay, thank you for listening, and that's it for today.